Hello everyone and welcome to our 6th video lecture. The topic for today is vector fields. Vector fields are functions which assign to every point in the real plane some two-dimensional vector. They're important because there are lots of natural examples. For example, the following graph assigns to every point in the Florida Gulf a vector representing the local velocity of the sea surface. We should ignore the color in this graph, which denotes the sea surface temperature locally, though we could note here that the direction of the arrows tends to be in the direction of constant temperature, and never going from high temperature to low temperature, or from low temperature to high temperature. In other words, they point in the direction of what are called isobars. This is a characteristic of these particular velocity profiles, which is common in geophysical fluid flows. Another example is the electric field E, created by a dipole consisting of a proton and an electron. A similar example would be a gravitational field generated by particles with various masses. As a formal definition, we say that a vector field f on R2 is just a function which takes in an xy value and returns a vector, p of xy, q of xy, or in terms of ijk notation, we rewrite that as pxy of I hat plus qxy of j hat. Sometimes we won't want to write down the of xy part, and just as shorthand, we'll write f equals p times I hat plus q times j hat. We've got this cool little symbol over the top here, which is just putting a nice cool vector hat on that guy, which reminds us that the function is actually vector valued. We can do a similar construction for R3, where we assign to every xyz value a vector p of xyz, q of xyz, r of xyz, or in terms of ijk notation, p of xyz I hat plus q of xyz j hat plus r of xyz k hat. Let's look at some examples. In this example, I have a vector field on R2, which sends to every xy value the vector x over the square root of x squared plus y squared, y over the square root of x squared plus y squared. We can graph a vector field by drawing different arrows at particular values. I start out by making some x and y axis, like so, and I'm going to make a grid consisting of some points that I'm interested in. And now at each grid point, I want to draw a vector whose magnitude represents the length, whose length represents the magnitude of the vector field at that point, and whose direction is in the direction of the vector field at that point. The vector field that I've chosen gives us vectors that are always unit vectors, so the lengths of the vectors that I draw in this particular case should all be the same. Their directions are always in the direction of the point xy, so they're in the radial direction pointing directly away from the origin. For example, at the point 1, 1, I'm getting the vector 1 over the square root of 2, 1 over the square root of 2, which is just a vector pointing in this direction. At the point 1, 0, I'm getting the vector 1, 0, which is pointing in the direction of the x-axis. Similarly, at the point 2, 0, I'm getting the vector 1, 0. And at minus 1, 0, I'm getting the vector minus 1, 0. Minus 2, 0, I'm getting the vector minus 2, 0. And similar for those points on the y-axis. And I'm just filling in the various values at these grid points that I've constructed with a vector that has the right direction and an appropriate magnitude relative to the other magnitudes that I'm plotting. We can really have a nice Bob Ross moment here, filling this in with happy little vectors. And this plot, once we've finished all those happy little vectors, gives us a nice idea of what the actual vector field looks like. Just like any such graph, we can fill in more detail by making our grid more fine. But at this point, we can also kind of guess a pattern. In particular, if I choose any random point, I'm going to end up with a vector of length 1 in this case, which points directly away from the origin. So if I wanted to fill this in a little bit more, with even more detail, I'm just going to get more and more vectors like this. So that's our first example of plotting a vector field. This will be a really important topic in particular when you study differential equations. When we're solving first-order differential equations, we can make a graph like this, and the solution of the associated differential equation comes from kind of starting with whatever our initial value is for that solution, and thinking about this as an ocean, where I flow in the ocean in the direction of whatever the local current's telling me to go. So in this case, my solution would just be flowing out this way. You'll talk about that a lot more when you study differential equations. Let's look at another example. To plot this, we again start by making our grid, and at every particular grid point, we're going to put a vector whose magnitude is represented by the length of the vector, and whose direction is the direction of the vector. Notice that the magnitude gets larger as we move outwards. So in order to make the graphic fit, I'm going to start out with fairly small arrows. At the point 1, 0, I get the vector 0, minus 1, which is a vector of magnitude 1 pointing in the minus y direction. At minus 1, 0, I get the vector 0, 1, which is same length but pointing in the upwards direction. At 2, 0, I get the vector 0, minus 2, so I should draw a vector arrow which is about twice the length of the previous one. And similarly on the left-hand side. On the y-axis, at the point 0, 1, I'm ending up with the vector 1, 0, which is pointing in the rightward direction. It's about a length of 1. And at 0, 2, I'm getting the vector 2, 0, so it's going to be about double the length again. And similarly down below, but pointing the opposite direction. So I can already see my vector field starting out as some sort of fan-like shape here, or a windmill kind of shape, and we can fill in the rest of the arrows similarly. Remember, the magnitudes of our happy little arrows should be dependent on the magnitude of the vector. So for this at the point 1, 1, I should have a vector whose magnitude is the square root of 2. So it should be a little bit larger than 1 and a little bit smaller than 2. So if we fill in all our arrows, we end up with a picture like this, which is showing that the vector field is kind of a whirlpool type shape. In the context of vector calculus, we usually describe a function, f, which is just a scalar valued function on R2, as a scalar field. The difference between scalar fields and vector fields mirrors the difference between scalars and vectors that we learned about when we studied vectors back in our previous calculus courses. One of the most common ways of creating a vector field is to take a scalar vector field and take its gradient. These kinds of vector fields are often called gradient fields. Specifically, a gradient field is a vector field which is the gradient of a function. Another name for gradient fields is conservative vector fields. So the next time you're arguing with your grandparents about politics, you can just say, "You don't agree with me because you're the gradient of a scalar field." This and other horrible jokes will be the feature of the lessons to come. Conservative vector fields are a prominent feature of a lot of different phenomena in physics. For example, electric fields are conservative vector fields. In particular, E is the gradient of V, where V is the electric potential. Gravitational fields are also another example, where here the force of gravity is the gradient of phi, the gravitational potential energy. A fun and a little bit less common example is certain fluid flows, such as flows which are in geostrophic balance. This occurs in certain parts of the global ocean where the local two-dimensional velocity has components u and v given by u equals minus g over f times h sub x and v equals g over f times h sub y, where here h is the local sea surface height, g is the gravitational acceleration, and f is a parameter representing the local Coriolis effect, having to do with the fact that the Earth is rotating. This is an example of a very natural vector field which is not a conservative vector field. So let's distinguish it in that fashion. In fact, this vector field is somewhat the opposite of a conservative vector field, in the sense that it's divergence-free, and we'll talk about a bit more about what that means in later lessons. In particular, we'll come to a result that says that every vector field will have a decomposition in terms of a conservative vector field and a divergence-free vector field. But for now, let's just remark that this vector field that we've just written in example 3 is not conservative, i.e. it cannot be written as the gradient of a scalar function. Now that we've introduced our main player for the whole chapter, I wanted to give a brief overview of kind of where we're going with things. As you might guess at this point, the main topic that we're looking at is vector calculus, which is the calculus of vector fields. A lot of motivation for the topics that we'll discuss comes from the idea that force fields are in particular vector fields. So if I remember ideas like work is the integral of force with respect to distance. This has already been explored in the case that I've got a force pointing in a single direction. For example, if I have a particle which is constrained to lie on a certain line, and when it's on this line, it experiences a certain force, and I want to think about how much work I need to do in order to move it from its position A over to some new position B, well then the work done is the integral of force, which is going to be in general a function of position, from the starting position to the ending position. But this picture can be a little bit more complicated in reality, because the force is actually going to be a vector. So when our particle here isn't constrained to lie on a single line, I end up with a bit more complicated problem. Here I've got some sort of particle in the xy plane, and I want to move it from A to B, say, but A and B are now points, along some path I've chosen. But it experiences some sort of force described by a force field, which again I can think of as some collection of arrows, one for every point. So one of the things that we'll have to do is figure out a way to calculate the same sort of integral, but over an arbitrary path in the xy plane, and keep into account how much force is in the direction of my path. This topic will be discussed further when we talk about line integrals. And certain special kinds of line integrals will have the very nice property that the amount of work done will be independent of the path we choose. These will specifically be the conservative vector fields, which gives rise to their name, and the independence of path has a nice physical interpretation in terms of conservation of energy. We'll also discuss surface integrals and find an analogous result there. These results will generalize to non-conservative vector fields in the form of Green's theorem or Stokes' theorem, which is sort of a higher dimensional analog. And we'll discuss all of these at length. We'll also talk about divergence and curl of vector fields, and try to point out some physical intuition along the way. But our next topic will be how to do line integrals. Specifically, I want to figure out how to integrate a scalar valued function over a particular curve, and as well as how to do a vector valued function and be able to calculate these integrals related to work in 2 dimensions or higher. And that's where we'll pick up next time. But for now, this is all for this lecture. So I'll see you guys then.